Hi guys, please like, share and subscribe. And if you want full course for any actuarial subject, visit theactuarialguy.com or WhatsApp on this number. Thank you.
Hello and welcome guys. In this video, we are going to be discussing discrete distributions in R programming. This is my first lecture on CS1B, and as usual, my approach is always intuition first principle first. So for a lot of these distributions, I will just be giving you the intuition that we have already discussed in paper A again, right? I will be revising those things in case you have forgotten them. We discuss the intuition, the logic for every line of code. I don't teach like typical coaching institutes where they would make you cram formulae, and that's my approach for paper A as well as paper B. Now, after completing this lecture, you should look at the PBOR exercises, the link to which I have attached in this video if you're watching it on YouTube or on my website. So that link is there. Practice those exercises, and I will also be covering some parts of past exam questions where these concepts are tested so that your concepts are fully clarified. Of course, this is the first chapter, and full length exam questions are just not possible here, so not covering those, but I will talk about some parts of the past exam questions. Thank you. Enjoy. Hello and welcome guys. In this video, we are going to talk about discrete distributions in R. Okay. So we'll be talking about how do you work with discrete distributions, various type of discrete distributions that we have discussed in paper A. What are the different functions that you have available, and then how do you simulate values from a discrete distribution, because simulation is a very important part of working with data in a programming language like R, so that you are also able to produce a sample from a particular distribution and then further process it in order to build your model, right? So firstly, let's just start talking about the first distribution that we have here, and that is the discrete uniform distribution. Now we know what the discrete uniform distribution is. It's where you have n number of outcomes with equal probabilities. So we have seen the PDF, CDF and all of that of the discrete uniform distribution. Still, I'll just show you once, and this will be a quick refresher for you. So this is your uniform discrete distribution. The most simple case of this that we work with is where h is equal to 1. So if you have b minus a plus 1 values going from a to b, imagine a is 1 and b is 6. That would make it a die, roll of a die, right? So the total number value of values is 6 minus 1, that is 5, plus 1, that is 6, right? So your probability function would be 1 by 6, right? Your moments would be half of b a plus b, that is your expectation. So that would be half of 6 plus 1, that is half of 7, that is 3.5, right? Your variance is 1 by 12 times 6 minus 1 times 6 minus 1 plus 2. Okay, so this can also give you the variance, right? And you have the MGF and all of that here. You have the probability generating function as well, but we won't be working with PGF and MGF. We'll just work with the moments and the probability function, and we'll try to compute probabilities and then simulate values from this distribution. Okay, so let's just dive right into it. So the intuition of a discrete uniform distribution is that all outcomes are equally likely, right? Firstly, let's work with the sides of a die. So you're rolling a die and you have a D, which is the outcome vector, right? And the possible outcomes are, or your state space, which is 1, 2, 3, 4, 5, 6. These are the possible outcomes, right? So if you print D, you will see 1 to 6, right? Now, how do you calculate the probability of getting a particular outcome or getting the outcome which is less than equal to a particular value? Basically, how will you get the PDF and the CDF values? That is what is being asked here, right? So if you want to see what is the probability of rolling exactly 3, okay, how do you get the probability of rolling exactly 3? That we obviously know is 1 by 6, right? Because it's one of the 6 outcomes. But to formally do this, the way to do this is that in the denominator, you will have all the outcomes, okay, total number of outcomes, which is the length of D, okay? So if you just run length of D, you will see it's 6, right? And in the numerator, we would run the length of D where D is equal to 3, okay? So that is how you write this, the syntax of this, right? And this you will see there's only one possibility where D is equal to 3, right? So in order to get the probability, you do favorable outcomes by total outcomes. So that will become 1 by 6, that is 0.16667, okay? Similarly, if you want to get the probability of rolling a value which is less than equal to 4, that will be the length of D where D is less than equal to 4 in the numerator, that is favorable outcomes, right? So there would be 1, 2, 3, 4. and in the denominator again total outcomes, which is the length of D, right? So if you run this, you will get 0.67, right? That is again 2 by 3 or 4 by 6, right? So that's how it works. That is your probability of rolling a value which is less than 4, right? If you wanted the probability of rolling a value which is greater than 4, greater than equal to 4, how would you do that? So you will just change this condition. We'll just make this greater than equal to 4, and then 4, 5 and 6, there are 3 values, so the probability would be exactly half. Okay, so this is how it works. Now that's for how you calculate probabilities, right? How would you calculate the mean and the variance of this, right? So you can directly take the mean and the variance of the distribution, which you will have to remember the formula of discrete distribution. The formula is not given in the in R, so you can just refer to your tables. But if you want to get the mean, your mean would just be equal to, you can either just take the mean of D, right? That's one way to do it, because all of them have the equal probability, so it will directly come out to be 3.5. Or you can just use the formula, which would just be equal to 6 plus 1 by 2. Okay, that is again 3.5, and your variance would be equal to, as we had checked in the tables, it will just be this formula. So it will be 1 by 12 times 6 minus 1 times 6 minus 1 plus 2, right? So if you run this, your variance is 2.91667. Okay, so that is your variance. So this is how the mean and the variance work. Now let's move on to the simulation part of it, right? This is the first simulation we are doing in R, so let me get into a bit of detail of it. See, the thing is that in exams, when you will be doing simulations, you would want your examiner to get the same output as you do, right? And simulation essentially means generating a random sample from a distribution. So how can your random sample be same as their random sample? That is, how can your random results be reproducible? So for ensuring this, R has a functionality called as the set seed functionality, which allows you to set a seed value. That is, this is the value where R knows that this is the sort of identifier for this particular sample generation, right? And every time you will put the same seed, you will generate the same sample. As soon as you change the seed, you will generate a different sample. It needs to be an integer value. But the value can be very, very large. The restriction is that, some very large number is the maximum cap for it. So you can put any value. And in the exam, your examiners will give you what is the seed that they want you to put. As long as you put the same seed, you will get the same result as they would in their answer sheet, right? So here, firstly, we set the seed as 77. That's what we are starting with. And I'll show you by changing the seed, the sample actually changes. And then in order to simulate, we use this function called a sample. Now, what are we sampling from? If you look at the help on the sample function, the first argument is x, that is what is the vector that you're simulating from, right? So it is a vector of one or more elements that you're choosing from. Then another argument we are putting is what is the size of the sample that you want, right? So you want to roll the die 100 times, right? Think of it like you're randomly rolling the die 100 times and noting what the outcome is 100 times, right? So R is able to do that on its own by using this function, and you use replace is equal to true. So the same value can be pulled again, right? So it's not like we're drawing one from a basket of balls and then that ball number 1 is not put back. When that is true, then replace would be false. But here, when you're rolling a die, it's not like you're taking away some outcome, right? So because you're not taking away any outcome, this is with replacement. That is, 1 can come again, 2 can come again, 3 can come again. Any value can repeat itself, right? So that's what we're saying by replace is equal to true. Otherwise, here you don't need to put the probability, okay? And when you don't put in the probability, it assumes that all outcomes are equally likely, which is true for a uniform distribution. I'll show you how to simulate for other distribution where every outcome has a different probability. But here, the most beautiful part is that all outcomes have equal probability in a discrete uniform distribution. So you don't need to bother a lot about what the probabilities are. You can just leave that argument as blank. When you leave it as blank, probability is taken as null and all outcomes are equally likely. Okay, so now let's generate the sample or the simulation, and then let's just print this sample. So if you'll see, all of these values, 100 values have been generated. The first time you rolled a die, you got 2, then you got 5, then you got 5, different values between 1 and 6 have been produced. And now if you want to just see a frequency table of this, you use this function called as table of S. Okay, so once you run table of S, you will see that you got 1 20 times, 2 16 times, 3 22 times, 4 14 times, 5 14 times, 6 14 times. If you add them up, you will get 100. Now they're not obviously equal because there is some sampling bias. If you would increase the size of the sampling bias would reduce. Let's say you simulate this 1000 times, then your sampling bias would go away, and it would change. It would reduce. So now you get very very close values for the number of values that have been generated for different sample points. There is obviously a difference. It's not completely even. It's not 167 for all of them, right? But it's very close now. And as you increase the sample size, the sampling bias will keep on reducing. But one thing you would notice, as long as your seed is 77, the sample of size 1000 will just be the same. Okay, now when I rerun this command, a different sample came out to be. So you would be surprised. I had told you that as long as the seed is the same, the sample generated would be the same. Why is this different? Okay, one thing you need to remember is that before running your sample function, you need to set the seed again. Otherwise, R will just take a random seed. Okay, so you need to set the seed again in order to reproduce the same sample. Okay, now let me run these two commands together. Okay, so now when I run these two together, I run sample with set seed. You will see that my sample is 169, 177, 176, 150, 155, 179 for values 1 to 6, right? As long as I will keep on running set seed just before this sample, I will get the same sample. See, so the same sample will keep on coming. Let me actually show you by running the table command with this as well. Yeah, yes, see, 169 to 179, the same sample will keep on coming. Every time the same sample is there. But if I don't run set seed again, then the sample would change. Okay, so make sure when you're running your sample function, you need to run the set seed command before it. Okay, that is something you need to make sure in order to ensure that your sample is the same, right? And as soon as I change the seed, let's say I make it even 78, the sample would change. Okay, so now if I run this, it's a different sample. Okay, completely different sample, right? So you need to ensure this. You can also set negative seed, and that's also fine. It just needs to be an integer value. Okay, so let me show you with minus 78 what is coming out. A different sample has come out. Okay, so that is how you use set seed in order to ensure that the same sample is reproduced, but always run set seed just before you run your sample line. And then if you want to run it again, run set seed again so that the same sample is reproduced. Okay, this is important to remember. Now what I'll do is I'll run this again. And then once we look at the table, this is our table for the seed 77. I was generating a sample of size 100 and not 1000. That is what I was originally doing. So let me do that. Right. And now I want to plot this on a histogram. So how do you plot on a histogram? That is the next question. So for plotting on a histogram, we have already learned about the plot function in our introductory lectures. For doing a histogram, you have a hist function. Okay. So hist is the function you use in order to plot a histogram. In this, you put your vector of the data as the first argument, which is S, and then you take your breaks, which is basically where do you want to break your histograms. Let me show you what happens if I just run histogram without the breaks argument. It's randomly breaking apart at 1 and then 2. It has values and there's a gap. Okay, it doesn't make a lot of sense. So you need to put the breaks in the middle of the bars, right? So I would want this the bar on 1 to be from 0.5 to 1.5. Then I would want the bar on 2 to be from 1.5 to 2.5. The bar on 6 will be from 5.5 to 6.5. So I need to take the breaks accordingly from 0.5 to 6.5. Right? That will be my breaks. So once I run this with breaks, you will see we get very, very clean histogram. The bar on 1 is, and if you compare this to the table, it just is what we had in the table. So at 1 you have 20, at 2 you have 16, at 3 you have 22, and then 14, 14, 14 for 4, 5, and 6. This is how you get a frequency diagram. That is a histogram in this case. Okay. In histogram, obviously your bars are joined, and when do you want to break them? You have to specify that to R. Okay. So that's how it works. Now, see, the thing is that we have calculated the probability of getting a value which is 3 on roll of a die, or value which is less than equal to 4 on roll of a die from the theoretical distribution. But you can also calculate that from this sample that you have generated, this random sample. Obviously the value would be different because of the sampling bias. Okay, so if I run this here, you get a value of 0.72. If you remember, when we had run this earlier based on D, the value was 0.667. So the difference here, based on the sample, it has actually calculated how many values are less than 4 out of the total number of values in S. S is our generated sample. Okay, same thing when we ran on D, which is our theoretical probability, it is 0.667. So obviously in case of a die, it should be this. And as you will increase the sample size, you will see that it tends to this value, right? But for small samples of size 100, you are getting 0.72, okay, which is good enough. But there's a sampling bias. Similarly, for 3, value being 3, what had we gotten? We had gotten 0.1667. So now if you run this based on S, you will get 0.22, okay? So what is happening here? Here, you're getting a value of 0.22, again 0.1667. Why? Because of sampling bias, right? Similarly, you can calculate the mean and the variance. These are called as the empirical means and empirical mean and empirical variance, right? And the probabilities we had calculated are empirical probabilities. Why? Because they are based on data, the data you have generated in a sample. The theoretical mean and variance, the theoretical probabilities were calculated just based on the distribution. You'll see the empirical mean and the variance, you'll see it is different from the theoretical mean and variance. Our theoretical mean was 3.5, but the empirical mean is coming out to be 3.28. And our theoretical variance was 2.917, but the empirical variance is coming out to be 2.870303. Okay, now I want to move on to talking about the binomial distribution. Now we know what the binomial distribution model is. It's the number of successes in a fixed number of n trials where you have the probability of success in each trial as p, right? Now for the binomial distribution, R has a lot of inbuilt functions, right? You won't have to do things from scratch like we did for uniform discrete distribution. Binomial has a lot of inbuilt functionality. So let's try and understand that. So first thing you do here is that you define your n and p, right? So let's say you're rolling a die 12 times, right? And rolling a 6 is success, right? So once you roll a die, if you get a 6, that's success. If you get 1, 2, 3, 4, 5, that's failure, right? So now you're trying to model X, which follows a binomial 12, 1/6 distribution. And X is the number of times you get 6 in 12 rolls of a die, okay? So let's define our N and P first, right? Firstly, let's see what is the probability of getting exactly 4 6s in 12 trials. So 4 6s and 8 other numbers. So 4 successes and 8 failures, right? How will you do this? See, if you remember the PDF of a binomial distribution, and if I quickly refer to the formula and tables book, you will notice that the PDF is NCR or NCX p to the power of x, q to the power of n minus x, right? So one way to calculate the probability is substituting x as equal to 4, right? N as 12 and p as 1/6, q will be 1 minus 1/6, right? Once you do that, you can get the probability, and that's how we do it in paper A, right? So you can do it here as well. So for that, you will have to use the combination function, which is the choose function. So choose n comma x, n and x are already defined here. N and p, n, x, all three have been defined, right? So you choose x from n, that is ncx, p to the power of x, 1 minus p to the power of n minus x, and this will give you the probability. Okay, very straightforward, very easy. But R has a built-in function to do this as well, which is called as d-binom. D-binom gives you the probability mass function of a binomial distribution. Okay, here you just give it 3 arguments. The first one is what is it that you want to calculate the probability of, how many successes. Second one is n, which is what is your total number of trials, and then p, what is the probability of success in each trial, right? Once you run this, you get the same result. So you can do it either way. Another way you can do this is, instead of using this choose, you can also use the factorial functions to calculate this. So that would be so instead of choose nx, you can use the factorial definition of your combination function, which will be factorial of n divided by factorial of x times factorial of n minus x, right? You can also calculate your choose function this way, and the rest of it remains the same, and that will also give you exactly the same answer. So you see, you get the same probability, right? So you can calculate this anyway, but d-binom is the most straightforward way, and this is replicable to most other distributions, right? So you have this d function for other distributions, other discrete and continuous distributions as well, and we will talk about that very, very soon, right? Now, if you want to calculate the probability of 4 successes, this is how you do it, right? The good thing about this d binom function is that you can apply it to a vector as well, not only a scalar, right? So this x value can be a vector as well, right? So what if you want to get the probability of anything between 0 to 12 successes, right? So instead of this x, you put x vals here, and x vals you define as a vector from 0 to 12, right? And then you run this prop vals, and if you print this prop vals, so you get the probability of 0 success, 1 success, 2 success, 3 success, 4 success, 5 success, so on and so forth, right? Obviously, this is very difficult to read. The best way to read it would be a chart. The best chart for this is a bar plot. So we will make a bar plot. What are we plotting? The first argument is your, so if I show you the help on this, bar plot. So the first argument is the height variable, okay, which is basically the y-axis, okay. So we want to put the probability values on the y-axis, right? And then you have the names argument, which we are putting in, which is what do you want the name of each bar to be, right? So here we would put the names argument as the x values, right? Our x values are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So that is what we are putting. Let me quickly show you this, right? This is something we defined, right? So it's going from 0 to 12, right? This vector. Then you have your x labels, which would be number of times you have rolled a 6. Y label is the probability, which is what we put in the height or the y axis, right? The main title is the binomial distribution with binomial 12, 1 by 6, and the color is blue. You can put in any color, right? Once you run this, you will see this graph, right? So now it's much more intuitive. The probability of rolling 0 6s is about 11%. The probability of rolling 1 6 exactly out of 12 is about 26 27%, right? It's 26.9%, so on and so forth, right? So this is how you represent the binomial distribution as a graph, and this is your bar plot function, okay? So remember this. So far we have discussed plot, we have discussed histogram function, which was hist, and now we have talked about bar plot, okay? So these I'm discussing these plotting functions one by one as well. You should keep on taking a note of them, okay? Now this was the probability of all of these outcomes. Now what if you want to get like the CDF, okay? What if you want to get the probability of rolling less than equal to 4 6s, right? So how will you do that? So one way is obviously you take your d binom from 0 to 4, okay, and you add them up, okay? So the probability of rolling, see again, as I told you, you can put in a vector here, right? Just how we did here. We put it from 0 to 12. Now we are putting it from 0 to 4, right? So probability of 0 successes, 1 success, 2 success, 3 success, and 4 success, right? You're going to add up all of them, right? So in order to add all of them, you just take a sum around your vector, right? The output is a vector, you take a sum around it, you'll get the total probability of less than equal to 4 successes, right? Which is 0.96365, right? So that's how it works. Now, this is to get it using the d binom function. You're just adding up the probability of less than equal to 4 successes, right? But there's a quicker way to do it, which is to directly calculate the CDF at 4 successes, right? So directly calculating the CDF at 4 successes would be, you can use the p binom function instead of d binom, okay? So this is the second binomial distribution function that I'm introducing after d binom. D binom gets you the probability mass function. P binom gets you the cumulative distribution function, the CDF, okay? So now here the argument is just where do you want the CDF? Again, just like d binom, p binom can also take a vector, but here we just want the probability of less than equal to 4 successes, right? So you can directly do this and you will get the same answer. So this is again 0.96365. The second argument is n, the third is p. These two are the same between p binom and d binom. The only difference is that p binom gives you the CDF value, right? So less than equal to 4 successes can directly be calculated. Now, similarly, if you want to calculate the probability of less than 4 successes, not less than equal to, less than 4 successes, right? How do you do that? So that is same as less than equal to 3 successes. Less than 4 is 0, 1, 2, 3, right? Which is less than equal to 3. So you run p binom again, but at 3 instead of 4, right? So you can do that as well. That is 0.8748219, right? Next is the probability of greater than 4 successes. Now, how do you get the probability of greater than 4 successes? That is 1 minus probability of less than equal to 4 successes. So 1 minus p binom 4 n comma p, right? So this is also something you can do this way, right? Very, very straightforward. This is one way to do it, because p binom by default gives you the CDF, which is the left side probability, okay, which is the lower tail probability, okay. So when you look at the distribution, you're looking to the left of 4 and adding up all of that probability, right? That is your CDF, less than equal to probability. And then when you want the greater than probability, you just say 1 minus that, right? Another way to do this is to put this argument which is lower tail as false. By default, lower tail is true. Okay. When you make it as false, what it starts giving you, P binom starts giving you the greater than probability. Mind you, not greater than equal to, greater than probability. Okay. So it'll just by default take 1 minus what P binom 4 comma n comma P will give you. The same thing will be given to you by P binom 4 comma n comma P, lower tail is equal to false, right? So it just gives you the upper tail, which is the greater than probability directly. Again, same answer, right? Similarly, if you would want then the greater than equal to 4 probability, right? How would you get it? Greater than equal to 4 is same as 1 minus probability x is less than equal to 3, right? So if you want 4 and more, you exclude from 1 3 and lesser than that, right? So this is how you can calculate that. So this is also very, very straightforward. Another way to do this would be P binom. You want greater than equal to 4, right? So that is same as greater than 3. So you can calculate this as, this is greater than 3. See, greater than equal to 4 meaning 4, 5, 6, 7, 8, 9, 10 all the way up till 12, right? So that is same as greater than 3, right? So what I'm calculating is probability x is greater than equal to 4, which is same as probability x is greater than 3, right? So I'll take P binom, I'll take it at 3, I'll put n and P, and now I'll say lower tail equal to false. Why? Because I want the greater than probability. Lower tail equal to false gives you the greater than probability. So this is greater than 3 probability, which is same as greater than equal to 4 probability. Again, you get the same answer, right? So this is how it works. How would you plot the CDF? Okay. So if you remember, within plot, we had an option to plot a type S function, which was the step function. CDF is typically plotted as a step function. So what you would do is you take your x vals, which is from 1 to 12. You are plotting that on the x-axis. Remember, the argument for the plot function are different, right, than bar plot. Okay, so if you see plot, scatter plot function or plot function, the first argument is x. Okay, if you see the bar plot function, the first argument that goes in is height, which is y. Okay, so this is different. So you always refer to the help on the function. So the first argument is x vals, which is 0 to 12. Okay, the second argument is what do you want to put on the y-axis, right? So y-axis here, in this case, I want to put in my CDF, which is P binom. Okay, P binom, which is my CDF at every value I want to put, right? I'm drawing the CDF function. What is the CDF at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up till 12, right? That's what I want to put. N and P stay the same. The type of function has to be step because you're putting the step function, right? X label, Y label, and main are intuitive. We have just written what we are trying to plot, and this is how you get your CDF, binomial CDF. Okay, so this is how you work with this. So yeah, this is on P binom. Then next function that you've got is the Q binom function. Okay, which is the quantile function. It's the inverse of CDF. Okay, in case of CDF, what you do is against every value you see the probability of less than equal to that. Okay, in the quantile function, what you see is you have the less than equal to probability, and you see at this quantile what is the value of the of my x, right? What is the 80th percentile value? What is the 100th percentile value? What is the 60th percentile value? What is the 40th percentile value? What is the 20th percentile value? What is the 90th percentile value? It's just the inverse of the CDF function, right? It's just defined in a way to get any quantile that can be percentile, quartile, median, anything, right? So the way to do that, think about it, is just the inverse of this function. And for that, you have the Q binom function. Q stands for quantile. Okay, so if you want the 90th percentile, what you would do is you would say Q binom at 90 percentile n comma p. Again, the first argument here is the percentile which you want, and then this will give you as an output what is the x value. So the 90th percentile value is 4. Okay, so if you would read against 90th percentile here, you will see that you are getting the value 4. Okay, so that's how it works. And if you want to confirm if this is correct, right, you would check the CDF. The CDF at 3 is 0.87. The CDF at 4 would be 0.96365, right? So the CDF would become 90% somewhere between these two. But because CDF is a step function, it would directly go from being 0.874819 to 0.96365, right? Q binom gives you the smallest value of x such that the CDF is greater than 90% in this case, or greater than whatever probability value you are giving, right? So what is the smallest value of x for which the CDF actually exceeds this value 0.9? That is 0.963, against which the value is 4, right? So the answer here comes out to be 4. Okay, so that's how you check it. If you want to calculate the median, as I told you, you have to put 50% in terms of the quantile, right? It divides the data into two parts, and it's the 50th percentile or it's the middle quantile, right? So that's how you calculate it, and the median is 2. Okay, if you want to calculate the interquartile range, you calculate the 75th percentile, right? So you take 0.75 here, right? And the 25th percentile, this will give you Q1 and Q3, and then Q3 minus Q1 is your interquartile range, right? Or you can do this in one line itself. You can just take Q3 minus Q1, right? So this is how you get your interquartile range, right? So all of these functions are very, very straightforward and very, very intuitive, right? Now the fourth kind of function here, which is R binom. Okay, we have discussed. We started with P binom. Sorry, we started with D binom. D binom gives you the probability mass function. P binom gives you the CDF. Q binom gives you the inverse of the CDF or the quantile. Now R binom helps you simulate values from the binomial distribution. Earlier we had used sample in order to simulate from the discrete uniform distribution. For binomial distribution, you have a dedicated function which is called as R binom. So we are starting by setting the seed in any simulation function. You have to first set the seed, and then the next thing we do is that we simulate 100 simulations. Okay, you're rolling the die 12 times, okay, but you're doing that 100 times, right? So you're actually rolling 1200 times, but each simulation is the number of successes you get on 12 rolls. Okay, so you're rolling 1200 times, but one simulation is how many successes did I get on the first 12 rolls, then on the second 12 rolls, which is 13 to 24th roll, how many successes I get. So that's what we have. So you'll get 100 sample points, which is the number of successes you got on each of these 100 sets of 12 rolls. Okay, NNP we have defined. Okay, so once you run this, you will get 100 values. Okay, so in the first set of 12 rolls, you got 2 successes, then you got 4 successes, then 2, so on and so forth, right? You will see high values like 5 here as well, so on and so forth, right? So 100 times I've rolled this. If you see that, if you make a table of this, in 13 sets of 12 rolls, you got 0 successes. You got 5 successes in just 2 rolls, okay, and you did not get any more successes than that, because if you would look at the probability function or even the CDF of this binomial distribution, you would see almost 100% of the probability is concentrated till 6, right? Like 99 point something percent probability is finished here. These scenarios are very, very unlikely, right? Getting 6, 8, 10 successes on 12 rolls of die is very, very unlikely, right? Now, the best way to visualize this, as we did earlier, is a histogram. Again, the function is the same. I go from minus 0.5 to 12.5 because my lowest value is 0, right? So I would want the first break to the first bar to be from minus 0.5 to 0.5, and then the last bar to be from 11.5 to 12.5. That's how I've defined these, right? And yeah, we made a histogram, right? So you see most of the values are concentrated here, right? There are no simulations which are going here. And now based on this, so here we have got the simulated frequencies of 100 simulations, right? In 100 simulations, how many successes that did I get in each set of these 12 rolls, right? Now, what I want to see and do is compare this to the theoretical or the expected frequencies, right? So for that, I can use D binom, right? D binom gives me the PDF, right? Or the PMF. So if I multiply that by 100 and I'm taking it at X vals, right? So it would give me, let me just show you what this D binom was quickly so that you don't get confused what is happening here. So these were all the probabilities, and once I multiplied by 100, it just shows me what was the expected or the theoretical number of simulations I was expecting here. So you were expecting, okay, I need to round this off so that it's very, very clear. Right, so you were expecting 11.22 successes, trials with 0 successes, 26.92 trials with 1 success, 29.61 trials with 2 successes, so on and so forth. This is what you were expecting. So you want to compare it against this, right? That's why you have multiplied, like, out of 100, how many successes, 0 successes I'll get, 1 success I'll get, so on and so forth, right? So that's what you're trying to do here, and you want to plot this on the same graph using the lines function. Lines will just add a line to this showing this D binom. So let me quickly show you what this looks like. You've just added a line chart here. You can use lines function to do this, and you've done the type as O. So O is this is over the dots. The line is going over the dots, and you've taken color is blue, right? So you see the theoretical expected frequencies were these, but the empirical frequencies that you got are represented by these bars. It's much higher in case of two success trials. We were expecting them to be about 29, but the value that you have gotten is 37, right? So it's so much higher, right, than what we were expecting. So that's how it works, and you can plot the theoretical frequencies here against the empirical frequencies, right? If you see the empirical probabilities, these are your empirical probabilities, right? If you compare them against your theoretical probabilities, here you will see that there is a difference, especially at the value 2, where theoretically I was expecting 30% of the trials to have 2 successes, right? But 37% have actually gotten, right, that. So how did I get this? I just took the binom and I rounded it to 2 decimal places, right? If you see the empirical mean, so all of my simulations are in S, right? So if I take the mean of S, you will see the mean number of successes in 12 trials has come out to be 1.82. And if you compare it to the theoretical mean, which would be NP for a binomial distribution, that's 2, right? So that's lower. That's the sampling bias, right? Similarly, variance, NPQ or NP1 minus P, and the variance of S, if you compare them, your variance has also come out to be lower than what you would have expected. Okay, now see, our mean and variance have come out to be different from what we would have theoretically expected. The law of large numbers says that as you increase the sample size, your empirical mean will converge to your theoretical mean. So this is something I want to show you. I want to demonstrate the law of large numbers to you. Okay, how do I do this? Okay, let's keep on increasing the number of simulations we are taking and see how the empirical mean is going. Okay, so how I'll do it is, firstly, let's set a seed and I will generate a very large number of simulations. So 2500 simulations I've generated as a part of S large. Okay, if I show you S large, there are 2500 simulations here, right? So ideally, if I take the mean of this should be very, very similar to the mean of the theoretical distribution, right? And what was my theoretical mean? See, theoretical mean is 2, and on 2500 simulations, you are getting the mean as 1.9992. Okay, so at large, it seems like the law of large number is holding. That convergence is happening once you get to 2500 trials, right? 2500 simulations. But how is it progressing towards that? Let's see. So what I'll do is, first let me create an empty vector of 2500 zeros. Okay, so that's what we have started with. Let's call it average. Okay, now I'll run a for loop and I will take the mean of first simulation, first 2 simulation, first 3 simulation, first 4 simulation, first 5 simulation, first 7 simulation, first 10 simulation, first 50 simulation, first 100 simulation, so on and so forth. I will take a running average. Okay, so what I'm telling R is that for I in 1 to 2500, okay, you take the ith average as the mean of S large, but you only take from 1 to ith value. Okay, so the first time I will be equal to 1, it will take the mean of first to first value, just the first value. Then the second time I will be 2, it will take a mean of first to second value. Then I will be 3, it will take the mean of first 3 values, so on and so forth. When the loop ends, it will take the mean of the all 2500 values. So we are calculating a running average, right? This is called as a running average, right? You subsequently take the mean of more and more number of values, right? And what we'll do is, I'll show you what this mean looks like. So firstly, let me actually run this for loop, okay, and take this running mean. Okay, and now if I show you this average vector, you will see that the mean is calculated for I goes from 1 to 2500. Okay, it's all of these values I've been able to calculate the mean. So the first one, the mean is 2, then it's 3, then it's 2.667, and it just keeps on going. It's not been able to print 2500 entries, so it has omitted 1500 entries. But if you see, if you take the tail of this average, you should be able to see the last 6 values, and that will show you that the last mean will actually be the mean of all the 2500 values. The last one is 1.999200. This is what we had seen earlier. Now what I'll do is I'll plot this trend of mean. Okay, so what I want to do is I against 1 to 2500. Again, recall the first argument of plot is the x axis. Okay, so 1 to 2500. So how many values am I taking a mean of? Then the second argument is the y-axis. So this parameter is the average. The type that I'm taking is a line. So I want to see how it goes as a line, right? And the title is law of large numbers. So if you see, this is how my mean is going. Okay, and it's sort of converging towards this 2. You see, the fluctuation has reduced a lot eventually. In the starting, there's a lot of fluctuation, but after almost 1500 values, it's steady at almost 2. Okay, if I just add a line of the theoretical mean here, see, this is your theoretical mean. So in the beginning, it's very far from the theoretical mean, it's fluctuating, but eventually it has converged. So this shows your law of large number, that your mean, when you take a large number of simulations, right, the mean converges to the theoretical mean. Okay, so this is something I wanted to show. Okay, now this was all on the binomial distribution, but we have a bunch of other distributions when it comes to the discrete type of distributions. One of the very good thing about R is that the functions are consistent across distributions, right? So you have the D functions, which are the density or mass functions in R, which is probability x is equal to x. And then when we go to the continuous distribution, you will get fxx functions using D functions, right? So for example, we had D binom, which gave the mass function directly. Then you have the P functions, okay? Example is P binom. It gives you the cumulative distribution function. It gives you the CDF, and you can also get the right tails in order to get the greater than probability. Then you have the quantile functions, which are your Q functions, okay? This gives you the inverse of the cumulative distribution function, and basically you can calculate any quantile using this. And then you have the R function, which is the random simulation function, which can be used to generate random numbers from a distribution. This is true across all distributions, and I will show you this shortly. Okay, so that's the next thing we are getting into. So now we have covered discrete, uniform, and we have covered binomial. Let's get to geometric, negative binomial, hypergeometric, and Poisson. Okay, let's do this. So all of this binom and all this is done. Law of large numbers is done. Okay, geometric distribution. So what does a geometric distribution represent? We know it represents the number of trials needed to get the first success, right? And you have the type 1 geometric and you have the type 2 geometric, right? So which one does R model? Let's talk about that. So type 1 geometric distribution models the number of trials till the first success. The type 2 geometric distribution models the number of failures before the first success. In R, type 2 geometric distribution is directly modeled, right? So we will work with type 2, and if you want to convert it to type 1, we can directly convert it, okay? So let's just try and see how this would exactly work. So let's say you're working with a geometric distribution where the probability of success is 0.25. Now, what is the probability of having 2 failures before the first success? Okay, so we would set y as equal to 2, and this means that there are a total number of 3 trials till the first success, because number of failures is just number of trials minus 1, because you're just talking about 1 success, right? So let me just visually quickly show this to you, and of course we've discussed this earlier, but I don't want any confusion in this regard. So if you want to model the number of trials until the first success, okay, so this is the first success. That means every trial before this will have to be a failure, right? So what does that mean? So if I am saying I want to model y as equal to 2, which is the number of failures before the first success, this is my random variable of interest. That's same as saying that the total number of trials till the first success, which is x, would be y plus 1, okay, which is the number of trials till the first success. Because out of these trials, you are only seeing the first success, that is one success, which is this one. Everything else has to be the failure, right? So the number of failures would be 1 lesser than the number of trials, and thus you can model the number of trials as number of failures plus 1. Okay, so that is how it works. Now based on that, the probability that there are 2 failures before the first success, that is the first success is on the third trial, is you let y is equal to 2, and then you use d geom. Okay, earlier we were using d binom for binomial distributions probability, calculating the probability that x is equal to 2, that is you get 2 successes out of n trials in a binomial distribution was done through d binom. Here it's done through d geom. right? So y is 2 and p is 0.25. These are the two arguments, and the probability is 0.1460625, right? If you are to calculate this probability from scratch, that is using the formula in the tables, it's 1 minus p to the power of y, because y failures and then 1 success, so that is p, right? So this is your same probability you get, but then this is just a more efficient way, right? Now if you want to just apply this djom function on an entire vector, you can do that. So you have assigned this vector which is y vals, which is from 0 to 20. So it will assess what is the probability of having 0 failures before the first success, 1 failure, 2 failures, all the way up to 20 failures, right? And then I'm plotting this on a bar graph. Again, very similar function. I've executed this earlier. Remember, the first argument into the bar plot that goes is the y-axis, right, which is the heights, right? And then you put names as whatever you want to put in terms of the x-axis, right? So these are values from 0 to 20, and these are their probabilities, the corresponding probabilities which I want on the y-axis. Okay, so once I plot this, you will see this is what your geometric distribution graph looks like. Then you can use pgeom to get the probability that you have at most 2 failures before the first success. Okay, so less than equal to 2 failures, right? So again, you use pgeom, you get 0.578125. If you want to get the probability that you have greater than 4 failures, right? So greater than probability is pgeom with the argument lower is equal to false. Okay, earlier you had the left tail argument, now you have the lower argument. Let me see what that earlier argument was called. So the argument's name may be different, you might need to check help on this, but yeah, you have very similar functionalities. So under this p binom, yeah, you had lower tail, right? Now you just have this argument called as lower, right, which is false, but very similar in terms of its functioning. Now you're getting the probability that you have more than 4 failures before your first success, right? So that's 0.2373047. You can calculate this normally and check if this is correct or not. Then if you want to get the quantile, you can use qgeom. So the 70th percentile, that is the smallest value of y, such that the probability of having lesser successes than y is greater than equal to 70%, right, will be 4. Okay, so if you will just look at the graph of the CDF, if you plot the CDF and you will see against 70%, you will find the value 4. Okay, so that's how it works. Then if you want to simulate values from this distribution, you set the seed, you use rgeom instead of r binom, right? How many simulations you want, what is the value of p, right? You can use the table function to see the simulation, right? And then you can get the empirical mean, compare it to the theoretical mean, right? Do all of those things that we have done earlier. So just going over this very quickly, because the functions are exactly the same, right? And we have studied the geometric distribution in a lot of detail in paper A, right? Then you have your negative binomial distribution. Again, R models the number of failures before the kth success. Okay, so the number of trials would be the number of failures plus k. Okay, so you can get to the number of trials that way. It essentially is modeling the type 2 negative binomial distribution, right? The intuition here, and we have seen this in paper A, is that if you are talking about having, let's say, 6 trials till the second success, what does that mean? That means out of these first 5 trials, okay, let's say 7 trials till the second success. So out of these first 6 trials, what will you have? You will have 5 failures and 1 success. And then the 7th trial would be the second success. This is the 7th trial, which is also the second success, right? So the probability that y, which is the number of failures before the second success, would be equal to 5. Okay, so that is probability that you see 5 failures before the second success is same as probability that the number of trials you see till the second success is 7. Okay, these two are the same, right? What is the relationship? X is equal to y plus 2, or whatever is the number of trials you're looking at, right? So x is equal to y plus whatever is the number of successes you're looking at. Here we were looking at second success. Whatever is the number of successes you're looking at, you just add that to y and you will get x, right? So it's the same logic as paper A, nothing new here, right? Seeing 5 failures before the second success is same as seeing the second success in the 7th trial. Okay, so that's what you have, and we are by default modeling type 2 negative binomial distribution. Now, you set p is equal to 0.25, you set k is equal to 3, k is the number of successes you want to wait for. The probability of getting 2 failures before the third success, right, can be calculated using this d binom. dn binom, that is the change. Okay, it's negative binomial, so it's n binom. First argument is what is it that you want to calculate the probability of 2 failures before how many successes? Before 3 successes, right? What is your k parameter? That's 3. And what is your p, which is the probability of success in one trial? That is 0.25, right? So this would be the same as setting x as equal to 5, because 5 is 2 plus 3, right? So that is very, very clear. X is equal to y plus k. Okay, so that's fine. You can also calculate this from scratch. Okay, how do you calculate this from scratch? In order to do this from scratch, you need to use the formulae which are given in the tables. So either you use the type 1 formula or type 2 formula, you will get the same answer. We have derived these formulae in the paper A of the course as well, right? So no matter what route you go, you will get the same result. Now, if you have to calculate the CDF of negative binomial, you use Pn binom instead of Dn binom, and that just gives you the CDF. So this is the probability that you will see at most 2 failures before the third success, right? So that's why we have taken this as 2. This is the less than equal to probability. The greater than probability you can calculate by putting this argument lower equal to false, right? Similarly, you can calculate the quantile, which is the inverse of the CDF, by using this formula, which gives you the smallest y such that probability y is less than equal to y is greater than equal to 0.6, right? So all of these are the same. You simulate these in the same way, and then you can calculate the empirical mean, compare it to the theoretical mean. All of this is the same, right? So you go through this. Negative binomial is also the sum of k independent geometric distributions, right? We know this because geometric distribution is trying to model the number of failures till the first success, and negative binomial is trying to model the number of failures till the kth success, right? So if you add k geometric distributions, you will get a negative binomial distribution. So one way to simulate it is also you can sum your geometric distributions, right? So you set a random seed and then you take your R geometric, which would just it has simulated these 3 values, right? So you're getting 0 failures, 8 failures, and 2 failures till the first success. And then if you sum them till the third success, how many failures are you seeing? 10 failures, right? So that's how it works. So that was all on negative binomial type 2 distribution. Now the next distribution that I want to talk about is the hypergeometric distribution. Now a quick refresher for you what the hypergeometric distribution is. So it's basically the same as a binomial distribution. That is, out of n trials, we are trying to determine the probability of x successes. The only difference is that we are dealing with a population which is without replacement here, right? That is, trials are not independent. Each subsequent trial affects the previous one. How does that happen? Let's say you have a deck of cards. Once you draw one card, either you would be drawing a black card or a red card, right? So your draw itself affects the next time you draw a red card or a black card, right? Because once you draw one card, if you've drawn a black card, then there are only 25 black cards left in the deck instead of 26. But the number of red cards is still 26. Then you draw another black card, you only have 24 black cards, right? So you're not replacing, you're not putting back that card that you've drawn from the deck. Okay, so that is how it works. Now let me just give you a quick refresher of how this distribution works, right? So if in a deck of 52 cards, I have 26 black and 26 red cards, right? And I want to find the probability of drawing, let's say, 4 black cards in 5 trials. What will this be? So this can be simply estimated using the favorable trials upon total trials, or favorable outcome upon total outcome formula, right? So what is favorable total outcomes? Total outcomes is that you're drawing how many ways you can draw from 52 cards. You can draw 5 cards. So 52C 5, right? And what are your favorable outcomes? That you draw 4 black cards, so 26 C4. Out of these 26 black, you draw 4, and out of these 26 red, you draw 1. Okay, so this is your probability, and this is how your hypergeometric distribution is characterized. So the generalized form of this would be, let's say you have a population of size n, and in this population the number of successes or the favorable outcomes that you have got is in this case it was 26, so you've got k favorable outcomes, right, out of this population of size n. So n minus k non-favorable outcomes, right, and you're trying to draw in a sample of small n, in a sample of size small n, you're trying to draw x successes, right. In our example, the population size was 52. The favorable number of outcomes in the population or the favorable observations were 26. The not favorable ones would be 52 minus 26. So again, this was 26. This was all your black cards. This is all your red cards. You're drawing a sample of size 5 and you want 4 favorable ones, that is 4 black cards, right? So how did we calculate this probability? It was, in the denominator I take NCN, right? That is choosing from a population of size n a sample of size small n, and then what are my favorable outcomes? Choosing out of these k favorable outcomes the x that I want, right, and choosing from this set of non-favorable outcomes, the non-favorable events, n minus k, I would want to choose my remaining outcomes, that would be n minus x, right. So I'm making this sample of size n. Out of this, I want x to be from k and n minus x to be from n minus k, right. So this is how it works. So that was your quick refresher on the hypergeometric distribution. Now how do you calculate these probabilities? Let's look at that. Let's take one example. Let's say you have a box with 20 chocolates in which you have 12 milk chocolates and 8 plain chocolates. Clear example of hypergeometric distribution. Once you draw a chocolate, the population of whichever chocolate you've drawn would reduce, right. Now let's say we eat 6 chocolates and we want to model x as the number of milk chocolates eaten, right. So out of 6 successes, a milk chocolate eaten on random draw, the number of milk chocolates eaten would be considered as success out of our sample of 6 chocolates, right. So here your n is basically your total population, capital N. K is the total successes that are present in the population, which is your 12 milk chocolates, right. And you're drawing a sample of size 6, right, which is your small n is 6, right. Now what is the probability that you have exactly 1 milk chocolate out of the six that you have eaten? Exactly 1 is a milk chocolate, right. So the other 5 would be plain chocolates, right. So the way to model this is d hyper. Whenever you're modeling a mass function, you use the d function. So here the d function is not d binom, it's not d n binom, it's not d geo, it's d hyper, because we are working with hypergeometric distribution, right. You want the probability for x, which is the number of successes being 1, right. Your number of successes in the population is 12. The number of failures in the population is the next argument, which will be 20 minus 12, which is 8, right. And your sample size is 6. So you give it these 4 arguments, it is able to give you the probability, right. So let me just run this whole thing actually. Right, so it is 0.1733746, and if you want to verify this, you can do this from scratch. This is the formula that I had just written on a piece of paper. Out of the n sample points that you are choosing from a population of size capital N, you want x to be out of k and you want n minus x to be out of n minus k, right. That's what we are doing. So this should be the same number, and it is the same number, right. This is how you calculate your probability. Now obviously you can put a vector in here instead of a scalar, instead of a single value. So if I put all the values from 0 to small n, that is 6, right. So we want to see the probability of getting 0 milk chocolates, 1 milk chocolate, 2 milk chocolate, 3 milk chocolate, 4 milk chocolate, 5 milk chocolate, and 6 milk chocolate, right. We want to see the probability at all of these values. So you take x vals as 0 to n, and then you run this probs vals as a d hyper, and you put x vals the vector, and you're putting so instead of x you're putting a vector now. K same, n minus k same, n is same, right. So if you run this, once you print your prob vals, you will see you get all the probabilities, right? So all of these are the probabilities of getting 0, 1, 2, so on and so forth, number of milk chocolates when you're eating 6 chocolates in total from the given population. Now you can obviously make a bar plot of this. Remember, bar plot, the first argument is the y-axis, so that's what you've put, and everything else is fairly standard. So this is your hypergeometric distribution. This is what it looks like on a bar plot. Similarly, if you want to get the CDF, so you use P hyper instead of D hyper, right? This is the probability of eating at most 2 milk chocolates, less than equal to 2, right? So that is 0.1372549, right? Probability of eating more than 4 milk chocolates. So you have this parameter here which is called as lower, you put it as false. So this is greater than 4, right? So all of these things are the same. Then you have the same Q hyper function which is able to get the 88th percentile, which is 4. So this is just the inverse of the CDF function, and then you're also able to simulate values from this hypergeometric distribution. From these simulated values, you're able to calculate the mean, and you compare it against the theoretical mean, which in this case is just your sample size multiplied with how many successes do you have in the population divided by the population size, right? So that's also 3.6. They're fairly close, and of course the difference is because of a sampling bias, right? Now next is you can approximate a hypergeometric distribution through a binomial distribution, right? Because the hypergeometric is same as binomial. The only difference is that in binomial, the population does not change. Each trial is independent, right? But in hypergeometric, the trial itself changes because of what you've drawn, or what the outcome of the previous trial is, right? So here you're approximating your P, which is the binomial theoretical probability. What is the probability of success in any given trial? So it will just be number of successes that you have in your population divided by the total population size. Here in this case, out of 12, there are out of 20, there are 12 favorable sort of outcomes. That is your milk chocolates, right? And that would just make it 0.6. Now what I'll do is I'll use d binom to actually get this probability, the same probabilities for x vals using a binomial distribution, right? So let's look at that first, right? So this is what your binomial distribution would look like, and to this I would add what my probability values are based on a hypergeometric distribution, which is what I had defined here. Prob vals was defined here, right? So this one. So I will add the hypergeometric one here. So you see hypergeometric is slightly different from what the binomial one is, right? So but binomial seems to be an okay approximation of this, right? So that's something to see, and then you can obviously add a legend to this, right? This is something we've discussed in the plot function. You can add a legend later, right? Which is what you're showing that this is my binomial approximation and this is my hypergeometric distribution, right? So that's what you've seen. So fairly straightforward, easy stuff here with the hypergeometric distribution. Next is your Poisson distribution. Now Poisson, we know what Poisson is. It's basically when you have infinitely large number of trials, right? So you're just observing events that are happening at a constant rate for a certain duration of time, right? And you want to figure out what is the probability that you will notice more than a certain number of events, right? So for example, goals in a football match, what is the probability that if at an average you observe 3 goals in an average match, what is the probability that you will observe 2 goals in a particular match, right? So probability of observing exactly 2 goals would be d Poisson, right? What has changed? Instead of d binom, you have d Poisson now, right? Which is 0.22, right? So this is just, if you calculate this from scratch, it's your standard Poisson formula, which is e to the power of minus lambda, lambda to the power of x divided by x factorial, right? Instead of lambda, we've taken m here, right? Same probability, but you can use the d Poisson function, right? Now, obviously, you can put in a vector instead of a single value, and you can plot it using the bar plot, right? So this is your bar plot, right? With all of these parameters going in. Then you use p Poisson in order to get the probability of less than equal to 4 goals, right? You get this argument which is lower is false, and you put it in p Poisson, you get greater than probability. If you want to get the quantiles, this is the 90th percentile, so it is 5. You can set seed and simulate. You can compare the theoretical mean with the actual mean, right? So all of that stuff you can do, nothing new here. You can also approximate your binomial n comma p probability with a Poisson distribution where n is very, very large and p is small, right? So this is something we've talked about earlier, and lambda is equal to np, right? So what we'll do is we'll compare Poisson 3 to binomial 10, 0.3. Of course, here n is not large and 3 is not, 0.3 is not a very small value for p. But eventually we'll get to binomial 100, 0.03. In all of these cases, they can be approximated using Poisson lambda, but the best approximation would come in this case, right? They all have np is equal to 3. But then, the best case is obviously where n is very large and p is very, very small, right? So let me just plot out the Poisson distribution first here. So we are plotting the values from 0 to 15, right? In a Poisson 3 distribution, what is the probability of observing 0 events, 1 event, 2 event, all the way up till 15 event, right? So this is what your Poisson distribution looks like, fairly standard stuff, and the plot function is also standard. We have used all of these functions that we have discussed earlier. The type is O, and you have these points over the line, and you've taken LWD as 2. You could have taken it as 5, and that would have changed the type of these this width that you have taken, right? So line width 2 looks much better, right? Now to this I want to add binomial 10, 0.3, 5, 50, 0.06, and 100, 0.03 lines, right? Using the dbinom function for the very similar values, right? Of course, you can't get more than 10 successes in a binomial distribution with n as 10. So we'll see how that comes out, right? But if you will see here, let me put in the legend and just show you what is happening. So here, if you see the red line, that's 10, 0.3, and it doesn't go beyond 10. It can't go beyond 10. Reason for that is you can't have more than 10 successes in a binomial distribution with 10 trials, right? But when you see 50, that is overlapping much better with the Poisson distribution. And when you see the blue line, which is binomial 100, 0.03, which is the largest n and smallest p, Poisson is able to approximate that almost perfectly. There's a perfect overlap between the Poisson line and the blue line, right? So Poisson is a great approximation for binomial as p tends to 0 and n tends to infinity when you have very, very large n and very, very small p, right? So that is what we were trying to show. And yeah, that's all for this lecture. Thanks a lot.